On problem 1, you need to use the formula that the speed of a wave is equal to the wavelength times the frequency. That means we can solve for the frequency by simply taking the speed of the wave divided by the wavelength. In this case, that's 340 meters per second divided by 0.19 meters. So the answer here is 1.79 kilohertz. The next problem, we have to use the fact that the direction of propagation of a wave is proportional to E cross B. So let's draw some axes here, the X, Y, and Z axes, and point the electric field in the direction of negative Y and the magnetic field in the direction of negative Z. And by looking at this and using the right-hand rule, you can see that the propagation direction must be in the positive X direction. Now in problem 3, we're given a side view of some observers, a light source, and a mirror. In this case, you have to use the fact that the angle of reflection is equal to the angle of incidence. So if we draw a normal to the mirror, and we consider the light coming from the source to the mirror, and we make the angle of reflection the same as the angle of incidence, we see only observer D will get light from the source. In problem 4, we're given a situation in which an interference pattern formed by shining a planar wave on a double slit arrangement is altered by putting a glass panel or a glass plate over one of the slits. So if we imagine putting some glass here, then the rays coming through and converging here will have different phases because this glass plate shifts the phase here by 180 degrees or pi. That, for example, means that in the forward direction, directly across where they normally would be in phase, now the ray from the bottom plate or the bottom slit will be 180 degrees out of phase, and you will get destructive interference in the forward direction, where normally you would get constructive interference. Likewise, you can think of the first point where you get, say, m equals 1. Normally, the two rays would be 180 degrees out of phase, but since you change the phase of one of them, that will bring them back in phase and you will get a bright spot. And following that argument, you realize that the bright and dark spots are interchanged. In problem 5, again you have to use the relationship between the wavelength, frequency, and speed of a wave. You can solve for the wavelength. It is the speed divided by the frequency. And since we know that the speed of light is 3 times 10 to the 8 meters per second, we can divide that by the frequency. And we see that the answer must be C, 1 times 10 to the minus 10 meters. In problem 6, once again, we're asked about the relationship between the direction of propagation and the direction of the electric and magnetic fields. So once again, we'll draw our X, Y, and Z axes, and we'll draw the vectors that we know. The propagation direction is in the plus X direction, and the magnetic field is in the minus X direction. And what direction is the electric field? Now, we know that the electric field cross the B field should give us the propagation direction, but if you look at this, you see that these are in opposite direction. The angle between them is 180 degrees. Now, in a cross product, the answer is perpendicular to either of the two vectors that are put into the cross product. So this combination of directions is actually impossible. problem 7 gives us two viewers and two observers and a object that they see. Now the lines of sight are to the object, or sorry, to the image of the object. So we can trace back those straight lines, extend those directions to determine where the image of the object should be. Now to determine the location of the mirror, we use the fact that the image location is located directly behind the mirror on a line which is perpendicular to the mirror, and the mirror is halfway between the image, this is the image, and the object. So that would be about right here, and perpendicular to that would be roughly this way. So this is the surface of the mirror. Now you can see that both of these observers are behind the mirror, so neither one of them could see this image. In the next problem here, you're given two diffraction patterns. One is from a diffraction grating with 100 lines per millimeter. The other is 200 lines per millimeter, but you don't know which is which. The way to solve this problem is you can reason from the formula that in a diffraction grating, the bright spots are given by this formula here, and you can see that the angle, as the angle increases, the spacing must decrease. Now the spacing is actually inversely proportional to this, so the angle then, if you think of it, the angle is actually proportional to the inverse of the spacing. So as the spacing inverse increases, you go from 100 to 200, the angle should increase. So that implies that the top spacing, or the top pattern, is produced by B and the bottom by A. In problem 1, you're given a flashlight or a beam of light that is directed onto a surface of water, and it diffracts down and hits the bottom of a pool. In part A, you must draw an accurate diagram showing the incident beam, refracted beam, and the labeled angles of incidence and refraction. So this is pretty straightforward. We just need to draw a nice diagram. There is my interface. There's my incident beam. We'll copy that again here, and we just remember that the incident angle is measured from the normal, and the refracted angle is measured also from the normal. Okay, now then, for the next part, I have to write down Snell's law using the variables defined in part A. So let's define N1 here and N2 for the water. So in that case, the law simply says the following. I can simplify this because the first beam, the incident beam, is in air, and that index of refraction is practically 1. So I can simplify this if I wish like this. Okay, the next problem. Use trigonometry to write down an equation relating depth of pool and the angle of refraction. So let me draw a simple diagram here. This is the depth of the pool, which I'm going to call h. The refracted beam is here, and this is the distance x. This angle is the refracted angle. So we can simply see that the tangent of the refracted angle is equal to the distance x divided by the depth of the pool. The last part is I need to solve these equations from B and C simultaneously to determine the numerical value of the angle of incidence. So let me just go back to my two equations, this one and this one. Let me just count unknowns and knowns here. The angle of incidence is unknown, and that's of course what I'm solving for. I know N2. I do not know the angle of refraction. That's theta 2. Actually, excuse me, there's a slight, that should actually be theta r, excuse me, as I call it, the angle of refraction. All right, so now we can solve for theta r using the equation from part C. It's the inverse tangent of x over h, which is the inverse tangent of 2.5 over 3.0, which is 39.81 degrees. Now we can use equation from B to solve for theta incident. Theta incident will be the inverse sine of n2 times sine theta r, which is the inverse sine of 1.33 times the sine of 39.81 degrees, which is 58.4 degrees. The first thing I'll do in this problem is draw another diagram. I'm going to draw the slits right here, and then I'm going to draw my screen over here, which is far away, and I'm going to draw a straight line here indicating the forward beam, which is a maximum in the forward direction. And the slits are very close together here. They don't really appear on this diagram, but they're spaced d apart, and that d is 5 millimeters. And then let's label the length L. Now the diffraction up to the spot, which is 10 centimeters up, I'll write that as 0.1 meters, is a minimum, all right? And the angle here, I'm labeling theta. Now this position right here we know is a forward maximum. It tells us that in the problem. But what about this position right here? What is it? Well, it tells you that the intensity is 0 here when it moves up 10 centimeters. So that's actually a point of destructive interference. So we have to use the formula for the conditions of destructive interference. So let me go ahead and write those down now. So that formula is d sine theta equals m plus 1/2 times lambda. So this term on the left is the path length difference between the two paths that come from the two slits that both go to this point here. This side is the requirement that the path length difference has to be a half integral number of wavelengths. So it has to be like a half a wavelength or 1.5 or 2.5, so that the two rays coming from the two separate slits are out of phase when they get there. Now, since this is the first point of destructive interference, as we move from the forward direction, which is a maximum, out, the path length goes uniformly from 0 up to the first point of destructive interference, which is when m equals 0. So we get a half a wavelength here. So this is the condition for destructive interference. So we can solve this for lambda, which is the what the question is asking us. To determine, it's 2d sine theta. There's actually one unknown here, the angle theta. We haven't really determined that yet. So we can do that easily using the geometry given in the problem. Theta will be the inverse tangent of x over L, which is just the inverse tangent of 0.1, which is 5.71 degrees. Using that with the formula that we just derived, we have the wavelength is 2 times 0.005 meters times the sine of 5.71 degrees, which equals 9.95 times 10 to the minus 4 meters, otherwise known as 1 millimeter to 2 sig figs. In this first problem, you have to use the total power emitted by the light bulb, and you divide by the area of a sphere with a diameter of 1 meter. Let me draw a picture of that. This circle represents a sphere at a distance of 1 meter from the light bulb. The light bulb is here at the center, so the light is coming out equally in all directions. So that power is uniformly distributed over this surface. So that implies that the intensity will be the total power divided by the area of that sphere, which is 4 pi r squared. That's 60 watts over 4 pi times 1 meter squared, which is 47.1 watts per square meter, or to 2 sig figs, 47. Just a correction, I did say that this sphere had a diameter of 1 meter. It actually has a radius of 1 meter, okay? The radius of the sphere is 1 meter, not the diameter. This next problem is quite easy. If the light bulb is only 10% efficient, then only 0.1 times the intensity above, of course, will get to the sphere or be converted to light, so that the intensity then would be 4.7 watts per meter squared. Alright, let's look at the next problem. To solve this problem, you need to use the following formula, that the intensity is related to the amplitude of the electric field by the following formula. Okay, where this is the speed of light and this is the permittivity constant, epsilon naught. So we can solve that equation for the electric field amplitude. Like that. So let's see what that gives us. 2 times the intensity, which is 4.7 watts per meter squared, divided by C, which is 3 times 10 to the 8 meters per second, times the permittivity constant, which is 8.85 times 10 to the minus 12, and the units are Coulomb squared per Newton meter squared. That is the formula, and that comes out to be 59.5 volts per meter, or 60 volts per meter to 2 sig figs. To solve this problem, I'm going to first do part B, and then I'll B and C, and then I'll do part A on the next slide. So in part B, we have to use the thin lens equation. Now the thin lens equation says that 1 over the image distance plus 1 over the object distance is 1 over the focal length here. Now we're trying to determine the image distance, so we can solve for 1 over di is equal to 1 over f minus 1 over d0. The focal length is 1 over 4 centimeters minus the object distance here. The object distance is 9 centimeters. This leads to an image distance of 7.2 centimeters. The image size can be determined from the following equation, the magnification equation. The image size would be equal to the magnification, which we know is di over do, the negative sign here, times the original object size. So this is 7.2 over 9 times 3 centimeters. Which is equal to 2.4 centimeters. Now the minus sign here is from that equation, but so we know that the size is inverted. So the actual size here is 2.4 centimeters. It happens to be inverted. That's what the negative sign indicates. Now we can determine the next questions, which are, is the image real or virtual? And is it upright or inverted? Well, we already determined that the image is inverted because our magnification comes out negative. Now, is it real or virtual? Well, because this image distance is positive, it's on the opposite side from the object, and that indicates that it's a real image, because rays from the object actually converge there. Here I'm going to do part A, which is to draw the ray diagram showing the image. So first I will draw a optic axis. So there's my optic axis. And I'm going to draw a lens plane here. So that's going to be my lens plane right there. And the foci. Now the focal length is 4 centimeters. So I'm going to count over 1, 2, 3, 4 and put a little X right there for the focus, and I'll do the same thing on the other side. So those are my two foci. And now the object is located at 9 centimeters over. So I'm going to count over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right here. And that object is 3 centimeters high. So I'm going to draw a line which is 3 centimeters high. Okay. Now the first thing I have to do is draw my principal ray number 1. Now what I'm going to do for principal ray number 1 is I'm going to draw a line which is a ray which is parallel to the optic axis through the lens coming parallel to the optic axis. Okay, the rule says an array parallel to the optic axis, when it passes through, the lens will bend towards the focal point. So let me draw that refracted ray going down through the focal point on the other side. Now the next ray I'm going to draw is one that goes through the focal point on the same side as the object. Okay, so that one is going to come down through here. Let me redraw that. So it hits the lens there, and then goes out parallel to the optic axis on the far side of the lens. Now the last principal ray will come from the tip of the object and will pass through the center of the lens. Okay, so there's my line, there's my ray that comes from the top of the object. It passes through the center of the lens and then intersects at the position of the focal point. So that focal point is right about here, and we have our image located right there. Now the labeling the foci, we have a focus here and we have an F prime on the opposite side. Labeling the object, here's the object and the image.